Which mathematical quantity links together information theory, machine learning, thermodynamics, game theory, the central limit theorem from probability theory, and many other areas of mathematics? The answer is entropy, one of the most important statistical quantities that you need to have a good understanding of, particularly with the rise of artificial intelligence the past few years. This video aims to clear the air on entropy and serve as a panoramic survey of where it appears in mathematics and a bit of history, and see how different areas of mathematics, which at first seem quite distant, are more related than you'd first think. I first came across entropy as an undergraduate studying the mathematics tripos at Cambridge. There's a course in third year called Codes and Cryptography, which sounds cool because it's got cryptography in the name. It doesn't have too many prerequisites either, and it's a little easier than some of the other courses like, algebraic topology. The codes part of the course actually turns out to be the even more interesting part in my opinion, covering information theory, as well as other topics such as error detection and error correction codes. I'll leave a link in the description to a great set of notes that follows the course, which inspired some of this video. So let's start. Our story today starts at Bell Labs in the United States. It's no exaggeration to say that Bell Labs is one of the most important organizations to have ever existed. There's an enormous amount of technology entered the world from there, and today we start in the year 1948. Claude Shannon, the mathematician, publishes his magnum opus, A Mathematical Theory of Communication, which gave birth to the modern information age. The paper covers the modelling of encoding, reliable transmission, and decoding of messages and their information. In fact, what do we even mean by information? It sounds at first like an abstract concept that Greek philosophers might talk about, but it turns out we can prescribe a mathematical formula for it, which is always a nice thing to do, and is what we'll work towards first. A code is a map C from an alphabet A to strings made up from another alphabet B, which we denote as B star. In our case, we're going to consider binary strings, ones and zeros. We encode a message M equals A1, A2, A3, say up to AN, as code words of A1 concatenated with the code words of A2, A3, A4, and so forth up to AN. And we transmit the encoded message over a communication channel, like a telephone wire or a fiber optic cable. A code is only useful if it can be decoded on the receiving end, unambiguously transforming the received stream of code words back into the message M. For a code to be decodable, it certainly has to be injective, but it turns out that that's not enough on its own. For a trivial counterexample, suppose that we defined a code on the English alphabet that encodes the nth letter as n zeros. Well, good luck, for example, decoding the sequence of 6 zeros unambiguously. Is it 6 A's? Is it 2 A's and 2 B's? Is it 3 B's? Is there a C in there? Is it just one big F? Who knows? One way to fix this would be add a terminating 1 to each code word, but this still seems very inflexible and wasteful. Even Hector Salamanca's code from Breaking Bad is more efficient.
A, E, F, A, E, I, O, U, A, B, C.
Yeah, we got it.
Let's try and see what properties are of interest when we're creating a code. Suppose we were to design a protocol for transmitting documents over the internet, in a simple case interacting with a single document that's on the server. We could create a code as follows. Suppose that the client connects to the server and sends the sequence 0, 1 to the server so far. Okay, we know they don't want to update the document since the stream started with a 0, but suppose the stream is silent for a few seconds now. The server cannot distinguish between the client wanting to get the file, and thus the client will not be sending any more data, or the client has a slow internet connection and has not yet sent the final 1 bit to delete the file. Thus, due to ambiguity, a deadlock has occurred. The problem we encountered with our protocol is that get code word was a prefix of delete. We could fix this by adding another 0 to the end of get code word. When receiving the bit stream, bit at a time, as soon as we have a candidate code word, we want to be certain that it corresponds to a code word transmitted and isn't the prefix of further data, so we can decode it immediately. A good, simple class of codes to consider, therefore, is prefix-free codes. A prefix-free code is an encoding of our alphabet A such that no code word is the prefix of another. Pretty obvious, right? For example, let's create a code on the four letters E, H, L, and O for a hello code. These are best visualized as a tree, in our case a binary tree for binary codes. The depth of the tree is the length of the longest code word. Observe that each code word forms a leaf node of the tree, the reason being that any further nodes under a leaf node would correspond to another code word with that one as its prefix, which we've mandated don't exist. To decode a bit stream, we receive the bits one at a time and we proceed down our tree. As soon as we reach a leaf node corresponding to a code word, we know we can decode it as that code word, since the bits aren't a prefix of another code word, and hence we decoded one of the characters. This property is known as a self-punctuating code. As soon as we have a candidate code word, we know it's the one we're looking for. Hence, if we received just 1 from our hello code, we know that the user has a slow internet connection, and we confidently wait for more data to follow, knowing that there isn't a deadlock. So it resolved that issue. One immediate inequality we can put forwards for our binary trees is Crafts inequality for the lengths of the code words of a prefix-free code. That is, the sum over all the code words of 2 to the negative the length of the code word is less than or equal to 1. So what does that mean? If we have a code word of length 1, for example E getting mapped to a single 0 bit, that code word must take up 1/2 of the tree. No further code words can exist with a prefix of 0. The H takes up 1/4 of the tree, 2 to the negative 2, and the L and the O take up 1/8, each having a code word length of 3. Overall, this must sum to no more than 100% of the tree. Conversely, suppose that we had a set of capital K numbers of integers, Li, corresponding to letters in our alphabet, and the lengths satisfy Crafts inequality. We can create a prefix-free code where each code word has length L_I. We first order the lengths from smallest to largest and allocate the code words one after the other in that order. The first code word can be of any length L1. For example, in this case, with L1 equals 1, we choose the left branch. For the next code word of length L2, e.g. L2 is equal to 3, Crafts inequality tells us that of the 2 to the power of L2 number of code words originally available, at least one of the 8 of them is available. And this process continues in a pretty obvious way. We can always fit more code words in if the lengths don't take the craft sum over 100% of the tree. In 1953, 5 years after Shannon's paper, Brockway-Macmillan published an article, The Basic Theorems of Information Theory, which among many interesting known results by Shannon, also includes a strengthened version of Crafts inequality that tells us any decodable code satisfies Crafts inequality. I'll leave the proof in the set of codes and cryptography notes I've linked in the description of this video, since there's not too much to visualize. But what this tells us is that for any decodable code, aka any code of any use, its code word lengths satisfy Crafts inequality, and therefore we can create a prefix-free code with those lengths. So from here on out, prefix-free codes are going to be our go-to set of codes. This is where things start to get really good, so thanks for being patient with the preliminaries. We now know how to construct a set of code words for an alphabet, given some code word lengths. But how do we choose the code word lengths? We'd like to make the codes pretty efficient. For example, there's no point in making our hello code to be like this, with 5 extra trailing zeros, or doubled up in bits. It's quite a waste. We want to make the lengths as small as possible. Perhaps that was obvious, but how do we compare the letters against each other to determine which one ends up shorter than the other? If we want to transmit a generic message in English via Morse code, the most common vowel in the English alphabet, E, is encoded as a single dit. So perhaps it's to do with the frequency of characters in our alphabet. Formally, we treat the alphabet like a random variable from probability theory, with probabilities of choosing each character as they appear in a body of text. We'll denote the probability of picking the letter A as P_A. The expected code word length of an encoded letter is therefore the expectation of this random variable, that is, the sum over all the code words of PA times LA. We want to try and minimize this quantity when we choose our code word lengths, with of course the code word lengths constrained by Kraft's inequality. So how do we go about this? Shannon puts forth the suggestion of setting LA to be the logarithm base 2 of the reciprocal of the probability of the letter occurring. If we remember our laws of logarithms, the log of 1 over p can be written as negative log p, which is a little less vertical of an equation to write out. Plotting a graph of negative log base 2 of p, we see that the probabilities closer to 1, aka the more common letters, have a shorter length, and the code word length increases monotonically as probability decreases, which is a sensible construction. In fact, this choice is more than just sensible, it's clever, since if we plug the code word lengths into Kraft's inequality, by construction, the sum of 2 to log base 2 of PA is equal to the sum of the PA, which is equal to exactly 1 since the PAs are a probability distribution. A slight final tweak is to observe that the logarithm of a number is almost never an integer. Hence, to make our code word lengths integers, we take the ceiling function of negative log base 2 of p. Now we have our code word length according to Shannon's method. So what's the expected code word length via Shannon's method? Overall, we have that the expected code word length satisfies the following inequality. So that's where that mysterious term on the left hand side comes from, which we've seen in the introduction of this video and the thumbnail. Again, don't let the negative sign fool you, it's actually a positive quantity since we're talking about logarithms of probabilities between 0 and 1. But what's the significance of this quantity? So far this is just an arbitrary term in an arbitrary inequality for an arbitrarily constructed code. Well, as it turns out, this left-hand inequality holds for any code with that probability distribution. We call this value the information of a probability distribution. Let's prove the information of a probability distribution is the lower limit on the expected code word length. This will be our first really significant result of the video. To do that, we'll need one more inequality, Gibbs inequality. Gibbs. That name may seem familiar to some of you. Josiah Willard Gibbs was a 19th century American mathematician and scientist. You may have heard of the Wilbraham-Gibbs phenomenon in Fourier theory, that is, the observation that the Fourier series strictly overshoots a discontinuity, no matter how many terms you use in the Fourier series. The example given here is a square waves Fourier series. You may have also heard of the Gibbs free energy in thermodynamics, a measure of the total energy a thermodynamic system can use. Albert Einstein described Gibbs as the greatest mind in American history. Pretty cool, right? He was one of the founding fathers of statistical physics, along with James Clerk Maxwell and Ludwig Boltzmann. A pretty impressive lineup. A key concept in statistical physics is entropy. The subject of this video, which we'll link back in just a bit. Right now we don't have to found an entire field of physics, statistical physics. All we need from Gibbs is the following inequality. For two probability distributions, Pi and Qi, each with the same number of values, the entropy of P, aka negative the sum of Pi log base 2 of Pi, is less than or equal to negative the sum of Pi log base 2 of Qi, with equality if and only if the Pi and Qi are pairwise equal. There's a couple of ways we can prove this. One is by observing that for any x, logarithm of x is less than or equal to x minus 1, the tangent curve to the log curve at x equals 1, with equality if and only if x is equal to 1. Hence, if we take a set of xi defined to be qi over pi, we can derive Gibbs inequality in the following way. Alternatively, we can invoke Jensen's inequality for the function negative log of x. The proof relies upon the function negative log of x being a convex function, which one can deduce from its positive second derivative. Letting each of the xi be qi over pi, just as we did before, Gibbs inequality easily falls out. Gibbs inequality is pretty simple but very powerful, and it'll be our best friend throughout the rest of this video. With it, let's prove our main inequality, Shannon's noiseless coding theorem. Suppose that we have a binary code on an alphabet A with probability distribution PA. We denote the code word length for A as L_A. Since the code is decodable, it satisfies the Kraft-Macmillan inequality. We let S equal the sum of 2 to the negative LA, which is less than or equal to 1. We form a set of QA for Gibbs inequality by letting QA be the proportion that the code word contributes to the Kraft sum, that is 2 to the negative LA divided by all of them, that is S. The left-hand side of Gibbs inequality is already what we want. The right-hand side expands out, the logarithms of the quotient expand into a sum, and we end up with two terms. The sum of the probabilities, PA, times the code word length, LA, aka the expected code word length, plus log base 2 of S. Since S is less than or equal to 1, log base 2 of S is a negative number. Hence the right-hand side is less than or equal to the expected code word length, and thus we establish our result, that the expected code word length is at least as great as the information of the probability distribution for our alphabet. This is a really non-trivial result, and is the birth of information theory. Any code we create and transmit encoded messages with must contain at least this expected code word length, this expected minimum amount of information per character to be decodable. Otherwise, the receiver would simply have not enough information to be able to decode the code words on the other end. For an example, using our hello code from earlier, we see that an expected code word length close to the information value of 1.846 can be achieved, but not less than that value. To transmit bits of information over a communication channel, we transfer bits of information. In fact, the computer science term bit originates in Shannon's 1948 paper on page 1. It's a portmanteau for binary digit, suggested to Shannon by John Tukey. A couple of remarks for this. You may have heard of Tukey if you've done some statistics before. For example, Tukey's post hoc test. He also co-invented the fast Fourier transform, a very useful algorithm indeed, and the box and whisker plot, who knew? Another remark to make is that Shannon's master's thesis a decade earlier in 1938 was on a symbolic analysis of relay and switching circuits, that is, using relays for digital logic circuits and how to simplify the circuits down. So that's probably what suggested Shannon to mention relays and flip-flops, bearing in mind that this was done before the transistor was first built in 1947, also at Bell Labs. Shannon's noiseless coding theorem tells us that we can't keep compressing and compressing data down. There's a mathematical hard limit on the minimum number of bytes we need, the minimum amount of information we can get away with. We also notice that the information of a random variable is independent of the values the random variable maps from and those it maps to, unlike, say, the mean and variance, which also take into account a random variable's values. A hot take to make at this point would be that information is even more fundamental and important than mean and variance. It seems to act maybe as a measure of randomness for a random variable, and hence we have another name for information: entropy. How random really is a random variable x? When I'm in need of some information, it's because I'm not quite certain of how an event is going to pan out. It may go one of several ways. There's a bit of uncertainty, a bit of randomness, a bit of entropy present, a lack of information on our part that is stored within the random variable. Let's consider a weighted coin flip, where heads has probability p and tails has probability 1 minus p. We can calculate the entropy of this random variable as a function of p, and plot it as a graph. We notice that for very small values of p, say 0.05, aka 5%, the entropy is pretty low, and we're confident that the coin is most likely going to land on tails. Indeed, for p equals 0, there is zero entropy. The coin is always going to land on tails, zero uncertainty. However, for a value of p close to 0.5, aka 50%, the coin flip is pretty fair, and for exactly 50%, a fair coin flip, entropy maxes out. One whole bit of information is required to encode the value of the coin flip, so entropy is equal to 1. This case of p equals 0.5 is usually what one means by a random, in quotation marks, coin toss, 50-50. Indeed, this maxing out of entropy generalizes for a discrete random variable taking n values. Let's use n equals 6. What's the most random possible probability distribution you can think of? where everything's so chaotic and entropic, where everything has the same chance of happening as anything else. Did you get it? The answer is the uniform probability distribution. To see that, let's employ Gibbs inequality, again with an arbitrary random variable x, setting all of the qi equal to 1 over n. We can take that out as a constant in the summation. All of the pi sum to 1, and so we're left with the right hand side of log base 2 of n. As we stated before, equality holds in Gibbs inequality if and only if each pi is equal to each qi. In this case, each pi is equal to 1 over n, aka the pi form a uniform probability distribution. Our example case for n equals 6 is a fair die. Log base 2 of 6 is about 2.585, and one way to interpret this number is as the minimum number of Boolean questions that are required to deduce the certainty of a value of a roll. It's a bit like the game of 20 questions or Guess Who or Akinator. In fact, let's play and roll the die. Okay, suppose I can't see the value the die has landed on and I have to guess it. Is its value greater than 3? No. Okay. Is my value equal to 3? No. Okay. Is it equal to 2? Ah, it is indeed. And if it weren't, then at this point we know with certainty it would be equal to 1. What was the average number of questions needed using this method? We can create a binary tree of questions to visualize our method. Ah, do you see the connection between prefix-free codes and decision trees now? The expected depth we traverse of this decision tree is equal to the number of questions we ask. There's a couple of ways we could count this, either by going diphase by diphase or layer by layer through the tree. This is akin to Riemann integration versus Lebesgue integration. I'm going to go layer by layer. We could guess 3 or 6 using just 2 questions. 1, 2, 4 and 5 took 3 questions. Overall, this gives us an expected number of questions asked as 8 over 3, or 2.6 recurring, which we notice is close to, but greater than, the value of log base 2 of 6, the entropy of the probability distribution corresponding to the die. You can't beat the value of entropy if you want to be absolutely certain, aka to guarantee we've extracted enough information, reducing the amount of entropy to 0. On average, the number of questions we need to ask is at least the value of entropy. A worse technique to guess the die's value would be to enumerate a random permutation of the possible outcomes one at a time, i.e., is the value 5? No. Is the value 3? No. Is the value 1? And so forth. Perhaps you'll get lucky and the correct answer first time, but intuitively we think this is going to be a worse technique. But how do we show that mathematically? Well, again, let's consider the expected number of questions. There's a 1/6 chance to guess the value with 1 question, a 1/6 chance to guess it with 2 questions, and so forth. And there's a 1/6 chance we guess the value with 5 questions, and finally, if we know that it's not one of the first 5 values, we've ruled it down to the last one, and so no final question is needed. This also gives a philosophical reason for why the longest 2 code words in any prefix-free code always have the same length.
To eliminate the impossible, whatever remains, however improbable, must be the truth. How poetic.
So the expected number of questions we needed was a total of 20 over 6, or 3.3 recurring, which is larger and worse than our previous technique, which had 2.6 recurring. It's so bad in fact it's fallen off the screen with these animations, so let me bring that down a bit. There we are. The first technique worked really well because we split the die into 1, 2 and 3, and 4, 5 and 6 in the opening question. We gained a lot of information with that first question, and was pretty much as close to a binary tree search that we could create. This method of interpreting entropy as a number of binary questions of course works for non-uniform probability distributions as well. I believe that 3Blue1Brown did a video on solving Wordle puzzles using information theory in a similar way. It's good to be able to interpret entropy numerically like this, instead of it being an opaque quantity. It's what we might want to call a white box quantity instead of a black box method like neural networks in machine learning. Speaking of machine learning, this gives us some inspiration for building decision trees, one of the most widely used families of machine learning models. The tree should be accurate on its training data, but not too overfitted, so that it still works well for its test data. The approach it takes is to try and maximize the information gained at each step, like our opening question for guessing the value of a die worked well, while keeping the tree depth relatively short to avoid overfitting, i.e. we don't ask too many questions or we might get confused trying to put it into practice. But what do we mean by information gain? How do we formulate that mathematically? Well, let's develop some more techniques for using information to our advantage. Let's investigate how the formula of entropy behaves when we extend it to multiple random variables. For random variables x and y, we can rather naturally extend our formula for information to be the information of x and y, h of x and y, is the sum over all values that x takes, all the values that y takes, of the probability that x is equal to lowercase x and y is equal to lowercase y, times negative log base 2 of that probability. It looks like a big formula, but there's really not much going on. Now, I call that the entropy of x and y, but really in probability theory terminology, this is the information of x or y, the union of x and y, if such a thing existed for random variables, sort of like the union of two events in a probability space. So to avoid linguistic hiccups due to the English language, we come up with some new terminology and we call this the joint entropy, or the joint information of x and y. Let's use a Venn diagram for ease. If we represent the information of x as the green circle on the left and the information of y as the blue circle on the right, then we interpret the joint information of x and y as the purple union. An immediate inequality we might want to invoke on this equation is Gibbs inequality, another Gibbs inequality classic. We set each qi to be the probability that x is equal to lowercase x times the probability that y is equal to lowercase y. This is known as the outer product distribution of x and y. These sum to 1, and thus we can plug them into Gibbs inequality. The logarithm of a product of two values splits into an addition of the logarithms, and we end up with two terms on the right hand side. Summing over y of the probability of x being a constant little x, and y being anything, gives us simply the probability of x, and vice versa in the second term, and thus we can simplify each of the terms on the right hand side. And what do you know, we have the entropy of x plus the entropy of y. And thus we've established that the joint entropy of x and y is at most the entropy of x plus the entropy of y. That is, the information contained in two information sources is at most the information contained in x plus the information contained in y. It's a pretty intuitive inequality. Gibbs inequality also tells us that equality holds if and only if, for each little x and little y, the probability that x is equal to little x and y is equal to little y is equal to the product of those probabilities. This is precisely the definition of x and y being independent random variables. In fact, let's go through an example in plain English. I know this might seem a bit childish, but having a simple example in plain English that we can parallel with our mathematical formulae allows us to make the mathematics simple too. Consider a king sending two messengers out of a castle to report on the kingdom, informants bringing information, The first one goes out through the courtyard and notices the flowers blooming. He then decides to go to the fields and sees the crops are growing. He then returns to the castle and reports to the king, the flowers are blooming and the crops are growing. The king then sends out a second messenger, who decides also to go via the route of the front courtyard and notices the flowers blooming. He then takes a different path and goes to the barns, where he notices the cows are mooing. He returns to the king and reports, the flowers are blooming and the cows are mooing. The king then says, well, I knew the first bit, but thanks for the news. We place these into our Venn diagram. The flowers blooming is information from messenger X, and so is the crops growing. From messenger Y we receive the repeated information that the flowers are blooming, and so we move that to the intersection of X and Y, and finally the cows are mooing is from Y. We can write our equations explicitly, and so we can express that the joint information of X and Y is in this case less than the information of X plus the information of Y, since X and Y aren't independent of each other. That is, there's non-zero overlap in our Venn diagram. Speaking of that overlap, just as we have the joint entropy for the union of two random variables, what about the intersection of two random variables? That is, the common information contained in both of x and y, which we call the mutual information, and denote with a capital letter I. So how do we express that? In probability theory, we know that the probability of A union B, where A and B are events, is the probability of A plus the probability of B minus the probability of A intersection B, since the A intersection B was double counted in the Venn diagram. We can rearrange this for the probability of A intersect B, and exactly the same for information. By our earlier inequality for joint entropy, we know that the mutual information is greater than or equal to 0, with equality if and only if the two random variables are independent. Compare that with probability theory, with two events A and B being called mutually exclusive if the probability of A and B is 0. Knowing information about one gives 0 information about the other. So in our King's Messengers example, the mutual information of the messengers is one copy of the flowers blooming. Let's clean this up. So this is what we have so far. There's one more, in fact the most important interaction, which we'll look at in just a minute. That is the conditional entropy. To approach that, we have to quickly consider another way to interpret mutual information. So far we've considered mutual information as the information in common with two information sources. Another use of mutual information is to see how much in common two questions have. Another example might be the weather. A GCSE mathematics problem for high school students might be, given the probability tree as follows, find the probability that the weather is rainy. They find that probability by finding the probability it's rainy given that it's cloudy times the probability that it's cloudy plus the probability that it's rainy given that it's sunny times the probability that it's sunny, which in our case is 0.69, at which point the examination room erupts into laughter for reasons we simply do not know. Then part 2 of the question asks along the lines of, using this value, show that the cloud coverage and rainfall are not independent events. It may be pretty obvious from noting that the two rainy versus dry distributions differ from each other, but it's an exercise in, does the student understand how to calculate probabilities? They demonstrate that the probability of cloudy and rainy is not equal to the probability of cloudy times the probability of rainy. We can go one step further and calculate the mutual information of the random variables of cloud coverage and rain coverage. We find out that they share about 0.348 bits of information in common. We can divide through by the joint information to see the percentage overlap of the random variables. Mutual information divided by joint information is always in the range 0 to 1. We see that it's around a 24% overlap. Knowing something about the cloud coverage tells us a little bit about the rainfall and vice versa, and we now have a way to express that mathematically. A measure of how much in common two questions have. The last and most important interaction to consider between random variables is conditional entropy. This all leads us on to machine learning, which is awesome. In our messengers example, the messengers arrived at different times. Suppose this time messenger Y arrived first, then X. Y gives us new information about the flowers and cows. Then X arrives, but really the only new information that X gives is about the crops. Can we find an expression for just the new information from messenger X given the information of messenger Y? Playing around with this Venn diagram, we could express this as the union of X and Y minus Y. That is, the joint entropy of X and Y minus the entropy of Y. We can expand this formula out, and again it looks beastly but it's really not. We first extend the entropy of Y to sum over all values of X's. Now we can contract these two sums together, arriving at this fraction within the logarithm. Now what is the probability of x is equal to little x and y is equal to little y divided by the probability that y is equal to little y? It's precisely the definition of the probability that x is equal to little x given that y is equal to little y. Conditional probability. Hence we call this conditional entropy. The next bit is a little ugly, but it simplifies down in a minute, so hold tight. We can expand over the outer probability of x is equal to little x and y is equal to little y into a conditional probability, and we adjust our summation notation. We notice that this set of terms is the entropy of x given y is equal to little y. In probability theory notation, we can form a random variable of x given that y is equal to little y, a marginal distribution. That is, the random variable for x now that the event y has unfolded. This is the form of the formula for conditional entropy that we most commonly use computationally, but what on earth does it mean and how do we interpret it? That's what we figure out now. There was another way that we could have expressed the area of conditional entropy on our Venn diagram before. We could have expressed it as the entropy of x subtract the mutual entropy of x and y. When we discussed mutual information, we considered two interpretations of random variables: the mutual information of two information sources, the mutual information of two questions. Now it's time to combine both of these together. What if x represents an information source? For example, a die that's about to be rolled, and we're trying to guess the value, or a game of Guess Who where I'm trying to guess the opponent's character. And y is a question that we ask to try and seek out the result, like, is my character wearing glasses? Is my character bald? Does my character wear a hat? At each stage it's in our interest to ask the question that has the most in common with the information source, that is, the one that maximizes mutual information, which in turn minimizes the uncertainty, the entropy left, given that we've asked the question. So as we ask questions one after the other, we end up with a sequence of random variables of decreasing entropy. If one wants to interpret this as a conservation law, we could say that the decrease in entropy of a random variable corresponds with us humans, or robots, machine learning models, gaining that equal amount of information. If that formula still isn't clear, don't worry. Let's do an example and build a decision tree classifier node from scratch. Suppose that we have a set of data at the feet length of 25 men and women. This dataset is labelled so we know whether a person is male or female from the training data, and we can use this for training a machine learning model. With our data, we want to build a classifier that can take in new test data points and using their foot length can return a prediction of whether that person is male or female. Just from looking at this data, it seems that men's foot length is larger than women's on average. Our approach is to try and find a critical foot length such that above this length we predict data points as male and below this as female. Let's do an order-preserving spreading out of this data along the x-axis so it's easier to view. This doesn't affect our method and it's easier to visualize all the data points in this way. The critical length is going to be represented by this red line and the capital letter L. We know it's going to lie somewhere around here. It won't be a perfect classifier, but there's definitely some worth in the information contained in our data, which we can use for our advantage. We formulate our problem in terms of conditional entropy. The random variable x represents the classifier trying to classify a new data point as male or female without knowing anything about them. The random variable y is the Bernoulli random variable, which is true or false, whether the foot length is less than or equal to the critical length or not. And the conditional entropy of x given y is the entropy remaining after we've asked the question about the foot length. The assumption we make about our model is that this training data that we're using is a representative sample of all of the data, and hence the test data is distributed in the same way. That is, if 30% of the training data lies less than the critical line, then the test data will also have a 30% chance of being less than the critical line. And say if 90% of the training data on the left-hand set is female, then 90% of the test data also will be female in that case. These are reasonable assumptions about a fairly sampled set of data. The entropy of x without any questions asked is 0.994, or 99.4% of a single bit of information. It may as well be 100%, a coin flip. Here's our formula for conditional entropy from before, and we add in an example critical line. The two values that the random variable y takes are true and false, the left and right hand sides of the critical line. For the critical line as it is here, 19 values lie to the left and 36 to the right. So the probability of y being true is 19 out of 55 and false is 36 out of 55. In the left hand set is 1 man and 18 women, and so the entropy is equal to 0.297 bits. The right hand side has 24 men and 12 women with an entropy equal to 0.918. So for a test data point, its expected conditional entropy is equal to 19 out of 55 times 0.297 plus 36 out of 55 times 0.918 for a total of 0.704. That's already a pretty good reduction from 0.994. To find the best critical value of L, we simply iterate over all the possible splits and choose the one that minimizes the value of conditional entropy. The height of the yellow dots on this plot is proportional to the conditional entropy. In our case, we notice this split right here minimizes conditional entropy to 0.614. Not bad. The left-hand set is almost pure, that is, consisting of just one class of values, women. And thus we have the critical foot length L is equal to 7.4 inches. If we performed more splits recursively on the two subsets either side of our split, and maybe if we had some more features like a person's height or the voice pitch that we could try and sort our data by, we could build a better classifier. Information is power. I also had a bit of a light bulb moment when I watched this animation play out. It reminded me of Maxwell's demon from thermodynamics, which we'll mention in a few minutes. Maxwell's demon is a thought experiment in which a divider is placed halfway through a room full of mixed up gas molecules, say oxygen and nitrogen. An intelligent pixie, or demon, opens and closes a door in the divider, letting oxygen through to the left room and nitrogen to the right room, so that eventually the gases are sorted out into two low entropy subsets, all the oxygen in one half and nitrogen in the other. Decreasing entropy like that, without doing any thermodynamic work, seems to violate the laws of thermodynamics. I know that our decision tree node isn't exactly the same setup. Instead of opening and closing a door, we're rather choosing where to place the divider, but there's definitely an inspiring connection here which I can't quite put my finger on, so let me know in the comments if you have any thoughts. So, from the decision tree classifier node to the decision tree classifier entire tree. I was considering making the decision tree classifier a separate video, but you know what, since we have literally all the tools we need to make it now, let's just do it. We're 100% the way there. Let's build a decision tree classifier for an actual real dataset, the iris dataset that I mentioned earlier. The dataset consists of 150 iris flowers, 50 setosas, 50 versicolors, and 50 virginicas. 4 measurements were taken for each flower, the petal width and length, and the sepal length and width. Here's what the petal and sepal actually look like for some context. Plotting a couple of these features, it looks promising that we could try and separate the classes of flowers from each other by considering some well-placed dividers that minimize conditional entropy at each step, as we'd just done in our previous example. I mean, look at those petal features on the setosas. We'll train our model on 80% of the dataset, that is 120 flowers, and we'll test it on the remaining 30 flowers. Our algorithm of choice is the ID3 algorithm from 1986 made by Russ Quinlan. It goes as follows. For a training dataset X, for each feature C in X, order X by that feature C, so as we did in our previous example by ordering the people by foot length. Find the critical value L_C for each feature, such that when we split X along that characteristic with that critical line, we minimize conditional entropy. And then we pick the best critical line from all of the features that minimizes conditional entropy. So the best possible split at each stage. And then we recursively apply this algorithm to both subsets on the left and on the right until we either reach pure subsets, that is, a set consisting of just one family of flowers, or we reach a maximum depth that we set manually. And that's it. It's a recursive greedy algorithm. So it's one of those algorithms where you say, you know what, I could have made that myself, but that's only because we now understand how to control entropy. So let's let it rip. We test each of the features one by one. Observe that there's only a few splits we can perform for each one. That's because there's plenty of repeated values in the dataset. lots of flowers with the same petal length, etc. The best initial split is on petal width, as we saw in the dataset pictures before. The left-hand side of the split is purely Satoza's, entropy 0, and so the algorithm terminates for that side. The right-hand side looks promising also, and I think you get the idea. So what we end up with is a decision tree. I coded my own decision tree for this video to make all of these animations in Python, and it's equivalent to using the scikit-learn package with the decision tree classifier, as you can see on screen. The decision tree classifier also has a couple of nice extra keyword arguments like min impurity decrease to make sure that the conditional entropy goes down at least that much for each split, aka we gain that much information for each split. This ensures that we don't end up with an overfitting model that creates a split just for one or two outlier elements. Testing our tree on the 30 flowers we set aside for the test data, the tree classifies 29 out of 30 correctly, so not bad, right? So congratulations, you just constructed your first ever machine learning model and we know exactly how it works. We didn't need the mean or variance of any of the features, just pure entropy. See what I mean when I said earlier, hot take, entropy is more important than mean or variance? It's possible. Running a decision tree classifier like this on the Iris dataset really is the hello world of machine learning for many people. Ronald Fisher, who created the dataset, was a biologist and mathematician himself, and came up with the idea of Fisher information, a distant cousin and forerunner to Shannon's formula for information. That being said, when did artificial intelligence really take off? It arguably goes back to Claude Shannon's 1948 paper, which is a real landmark in mathematically formulating some pretty abstract concepts like information and communication. After all, what is intelligence other than the acquisition of information and using that to better achieve a goal? Shannon's noisy coding theorem also tells us how much signal degradation a communications channel can tolerate for transmitting information efficiently. You can read the Wikipedia articles for History of Artificial Intelligence yourself, but I'd like to point out this nice article for Vogue magazine from 1963, an interview with Shannon. The man-machines may talk first to Dr. Shannon. The man-machines. Artificial intelligence. It's a pleasant read and gives an insight into Shannon's character, and I'll leave a link in the description to it. The article mentions Theseus, the mouse who learns a maze, that once amazed Bell Labs by learning its way down the alleys to a brass cheese. Although built just for fun, it was an early example of machine learning.
This is Theseus. Theseus is an electrically controlled mouse. He has the ability to solve a certain class of problems by trial and error means, and then remember the solution. In other words, he can learn from experience. Like his classical namesake, Theseus has the problem of finding his way through a maze. His objective is the goal here in the corner. He is now exploring the maze using a rather involved strategy of trial and error. As he finds the correct path, he registers the information in his memory. Later, I can put him down in any part of the maze that he's already explored, and he'll be able to go directly to the goal without making a single false turn.
Nowadays, with grandiose convolutional neural networks and large language models, one might overlook a maze solver as being intelligent, in quotation marks. But really, any device that improves itself over time by reducing entropy and uncertainty could be considered intelligent. Shannon was also into chess computers. A lot of great computer science work came from people who just wanted to play chess against a machine. Claude Shannon, Ken Thompson, the creator of the Unix operating system, and UTF-8, the lovely prefix-free encoding of Unicode text, and Ross Quinlan, who invented the ID3 decision tree classifier algorithm that we just used. Earlier this year, Anthropic also released Claude 3, their large language model, named in honour of Shannon. So let's ease off a bit now. With a good understanding of joint, mutual and conditional entropy, we're ready to conquer the final section of this video. Let's revisit the binary communication channel that encodes just two characters, say A and B, or heads and tails, with probability P for letter A. In the case that P is equal to 0.5, the entropy is negative log base 2 or 1/2, which is equal to 1. So there's no possibility to cheat and send less than 1 bit per character. But what if p is not equal to 0.5 though? Say p is equal to 0.2. Well, the entropy is only around 0.722, which is much less than 1. Choosing an encoding for just A and B on their own, the best expected code word length we can create is a code of length 1, sending A to 0 and B to 1. And that's independent of P. Generating a random sequence from this alphabet for P equals 0.2, it seems like blocks of 1 are quite common, so perhaps we could get creative and create a block code in quotation marks and introduce compression. When encoding and transmitting a message, M equals A1, A2, A3 and so forth, over a communication channel, how about we divide the characters into fixed size blocks, like placing dividers between shopping on a conveyor belt? In our case, we'll take R is equal to 3. Consider the probability distribution that arises from taking a sequence of R characters. We notice the probability of transmitting the block 111 corresponds to BBB, which in our case is over 50% chance. If we consider the entropy, the minimum expected code word length of this code, x dash, it's equal to the joint entropy of R copies of x. By Shannon's noiseless coding theorem, we know that an optimal code for x dash satisfies having an expected code word length of no more than 1 plus the entropy of x dash. If we assume that the individual characters within a block are chosen independently of each other, we know that the mutual information of R copies of x is equal to R copies of the information of x. Here's where it gets clever. The expected code word length of a code for x dash is transmitting R characters from the alphabet in a block. If we consider the expected code word length per character, aka dividing this inequality through by R, look at what we have on the right hand side. We've managed to reduce the upper bound from the entropy plus 1 to the entropy plus 1 over R. This tells us that we can create better and better codes for larger and larger values of R. For example, our binary code with P equals 0.2 and R is equal to 3, using a Huffman tree, we can generate a code with expected code word length of 0.728, which is pretty close to the value of entropy of 0.722. This is one technique in achieving lossless compression, which is a pretty awesome thing. If we had a file on a computer with lots of repeated strings of characters, we could compress it down in this way. Block codes are one way to construct, shall we call, a multi-character alphabet from a code for compression purposes. More advanced techniques exist as well, such as LZ77, Lempel and Zeev's 1977 sliding window method, which looks for sequences of longest length repeated within a window of the input data stream, usually around 32 kilobytes. Both gzip and zstandard compression tools use a combination of LZ77 plus Huffman trees. You probably use gzip every single day without even knowing it. A lot of HTTP requests are automatically gzipped. According to Wikipedia, gzip is based, and I agree, so let's put it to the test. Let's do a random walk experiment in Python. We consider a grid of cells in a plane, say 40 by 40, where each cell has 0 or more molecules. We give the grid an initial population of molecules densely populated in one area, in our case at the middle of the screen. We'll represent the number of molecules with a base 64-ish counting system. We increment time in discrete steps, one increment after the other. Each increment we apply a random walk rule to each molecule. There's a 10% chance the molecule moves to the cell above, 10% that it moves to the one on the right, 10% to the one below, and 10% to the one to the left, and 60% chance that it stays where it is. It's a Markov chain. For computational simplicity on my end, I'm allowing the grid to wrap around like a torus as well, like Pac-Man's geometry. This is a fair random walk with no particular bias to any direction. Let's see how it evolves. As perhaps expected, the initial concentration diffuses throughout the entire grid, becoming more and more chaotic, more and more random, more and more mixed upness, more entropic. Mixed upness is the word that Gibbs used, sort of as a forerunner to the word entropy. To formalise this, what if we asked gzip to try and compress each grid down to as small a size as it can for every single frame? If we plot the size of the zip files over time, it's apparent that the size is generally increasing, As the grid becomes more and more cluttered, there's less and less repeated blocks that can be used to construct an efficient encoding of the state of the system, i.e. the expected amount of information required to keep track of everything is increasing. Making an empirical observation and conjecture, it seems that on average entropy either stays the same or increases, the second law of thermodynamics perhaps. In thermodynamics, the formula for the Gibbs entropy of a system is, surprise surprise, of the form as you see on screen. Up to a factor of multiplication by Boltzmann's constant and using the natural logarithm, it's the exact same formula as in information theory. The pi correspond to the probabilities of microstates occurring, that is, how the particles in a gas are arranged, like our grid experiment we just did. Boltzmann's principle states that all of the microstates are equally as likely as each other, i.e. the pi are a uniform probability distribution. There's so many particles going on in the gas and so much movement that any microstate is equally as likely as another. As we've seen before for a uniform probability distribution, entropy is of the form S is equal to the Boltzmann constant times the logarithm of capital W, where capital W is the number of microstates possible. This is the form of the equation that appears on Ludwig Boltzmann's epitaph. In our experiment, as the gas diffused throughout the grid, it covered more and more cells, more and more possible microstates became possible. Looking at our graph on the right hand side, we know that entropy is a lower bound on the zipped file size, and it looks like it could be growing logarithmically. This would make sense in a Brownian motion experiment like ours, where the average displacement of a molecule from its original cell is proportional to the square root of the time elapsed. So we're on the right track. Now notice that the symbol for entropy here is a capital letter S and not the capital letter H, or really a Greek capital letter eta. There's a few technicalities such as staying away from quantum mechanics and Boltzmann's H theorem, which I think I'll leave for a better qualified physicist to handle, but the long and short is that thermodynamic work entropy and thermodynamic order versus disorder entropy are very much related, and Boltzmann's H theorem was an attempt to prove the second law of thermodynamics. There's plenty of thermodynamics content already out here on YouTube, so the intention of this video is to get a good understanding of the numerical value of entropy in a broader range of mathematical fields. I will end off this section though by saying that the number of microstates possible can be obtained by lots and lots of factorials and combinations, and if I'm correct, Maxwell and Boltzmann came up with a continuous probability density function for ease of an emergent distribution. I find it pretty impressive that Gibbs, Boltzmann and Maxwell were able to deduce these equations and formulate thermodynamics this way round. That is, thermodynamics coming first in the 19th century and then information theory in the 20th century. We have the advantage of hindsight to approach this in the other way round as we've done in this video. It sure seems easier to me to get an intuitive feeling of entropy from binary codes and random variables, then move on to thermodynamics and microstates, than it is to do that the other way round. This leads us on to our final section. Let's try and extend entropy from discrete random variables to continuous random variables, as Shannon did. With continuous random variables, it doesn't make sense to talk about, say, a person's height being exactly 1.8 meters to the absolute atom. Instead, we use a probability density function, p of x, and we integrate around a non-zero width, say 1.75 to 1.85 meters. In a similar way, we adapt the formula for entropy as Shannon did in his 1948 paper. We swap out the summation sigma for an integral, evaluated over the entire domain of the probability distribution, and there we have it. Now, the astute among you may notice there's a slight issue with the units of this equation. I know, physics and units, we usually don't do that in mathematics, but probabilities for discrete random variables are unitless scalars, whereas with continuous random variables we have units per volume. So that integrating over a volume dv, we end up with a scalar. Now the p on the outside here is fine, but the p on the inside of the logarithm doesn't have its units accounted for. So is this even a well-defined quantity? We just naively extended the formula from discrete random variables to continuous random variables. We call this the formula for differential entropy to distinguish it from entropy in the discrete case. It turns out this is an okay thing to do if we get Gibbs inequality to help us out. Good old Gibbs inequality. If we subtract the differential entropy from negative the integral of p times log of q, where q is another probability density function, we end up with a ratio of probability density functions inside the logarithm, which is a unitless quantity, and so units wise everything is good. This quantity is greater than or equal to 0 by Gibbs inequality, which also holds in the continuous case. We've met this quantity before for the inequality in the discrete case, and it turns out that it has a name. It's called the Kullback-Leibler divergence. Very strange notation for it, but yes, it has a name. So it makes sense to talk about the Kullback-Leibler divergence of two probability density functions, and we sort of risk it a bit and split this logarithm back up into its two constituent parts. We've met this before. The left, of course, is the differential entropy, and the right-hand side also has a name, the cross-entropy of P and Q. No, not cross-ent, cross-entropy. Though I often just call it the right-hand side of Gibbs inequality, but it's good to find out these things have proper names, right? So let's investigate differential entropy, as some results from discrete random variables don't carry over, and there are a couple of extra new remarks to make. Remember the most entropic probability distribution in the discrete case, the uniform probability distribution. Well, that holds well for a finite set of values, but what if we consider the unbounded continuous case? That is, a random variable defined on the entire real number line. We can't define a non-zero constant probability density function on the entire real number line, otherwise the area under the curve is infinite. We could start with some inspiration from our random walk grid from the previous section. We start off with a uniform probability density function on the interval 0, 1, a nice small compact interval. How about we consider the cumulative effect of n steps of the motion? For n equals 2, we need to add together two uniform probability density functions. To do that, we take the convolution of the two distributions, which is a glorified form of addition for probability density functions, which yields a triangle-looking distribution. This is analogous to 7 being the most common value of the sum of two dice, say in Monopoly, and 6 and 8, and 5 and 9, and 4 and 10, either side being less common, symmetrically distributed. What happens if we add in another copy of the motion? We end up with a density function that has three quadratic regions. It goes up a bit, then down a bit, and then tails off. That shape may look a little familiar. If we add in more and more, we end up with a distribution which is ubiquitous throughout statistics and nature. The bell curve, the normal distribution, the Gaussian, however you want to call it. So that's one way that you can obtain the bell curve. But what does entropy have to do with it? It turns out that among all the probability density functions we can define on the real number line, with the same mean mu and variance sigma squared, the normal distribution has the most entropy out of all of them. Who'd have thought that when we add together maximally entropic distributions for the compact case, the uniform probability density function, we end up with a maximally entropic distribution in the unbounded continuous case? It's not too hard to prove this. We approach it in the same way as the discrete case, invoking Gibbs inequality. Let P be any probability density function with mean mu and variance sigma squared, and let Q be the normal distribution with mean mu and variance sigma squared. We focus on the cross-entropy, the right-hand side, and we break it up. We use our laws of logarithms to split the leading constant from the rest of the formula, cancel out the logarithm with the exponential, and we end up taking out a few constants and we're left with just two integrals. We use three properties. One, that the integral of p over the reals is equal to the integral of q over the reals, which is of course true for any probability density function since the area under the curve has to add up to exactly 100%. So we swap the first p for q. Property 2 is that the mean of p is equal to the mean of q, and 3 that the variance of p is equal to the variance of q, which we demanded earlier. So for the second integral, which is the definition of the variance of p, we can also swap out p for q. And now we can repack this equation back up, and what do you know? We have the differential entropy of the bell curve. So the differential entropy of P is always less than or equal to the differential entropy of the bell curve Q, aka the bell curve maxes out differential entropy. So what can we do with this knowledge? We can tackle the big one, the central limit theorem from probability theory. The central limit theorem states that for n independent identically distributed, or IID, random variables, the distribution that the sample average takes tends towards the normal distribution as n tends to infinity. That is, the more and more elements we have in our sample, the more and more the sample looks normally distributed. So for this, there's one final little lemma that we're going to use, and that is, how does the entropy of a convolution of two random variables relate to the individual entropies? It took me quite a bit of Googling to find this result, but I knew, as a mathematician, I just knew intuitively. I had that itch telling me that what I was looking for was the right thing, and I ended up finding it. The entropy power inequality, which has this unfortunately small Wikipedia article for such a really non-trivial result. Though it turns out that I could have found it in Shannon's 1948 paper to begin with if I'd looked a little more carefully. The entropy power inequality tells us that the power, or exponential, of the entropy of x convoluted with y is greater than or equal to the sum of the exponentials of the individual entropies. And therefore, certainly, we have that the exponential of the entropy of x convoluted with y is greater than or equal to the exponential of the entropy of x. And thus, taking logarithms of both sides, we see that the entropy of x plus y is greater than or equal to the entropy of x. Like our example with the gases before, we could consider x to be the probability density function of the particles distributed, and y could be the random Brownian motion convolutional kernel. And at each stage we're adding in more and more random motion. In computer programming style, we might want to write this as x plus equals y. At each stage we're adding on a copy of the Brownian motion convolution kernel. The entropy power inequality tells us that entropy only ever stays the same or increases. It's the second law of thermodynamics put into mathematical form. This is really what Boltzmann probably wanted to prove with his H theorem, mathematically formalising the second law of thermodynamics and proving it once and for all. I'm not going to prove this lemma, but you can have a look through Shannon's paper if you want the gory details involving multivariate normal distributions, but it's the intuition that counts. Now we can put this towards our main result. We have a set of n IID continuous random variables, and let's call x hat underscore n the random variable of adding the n random variables together and dividing by n, the average. X hat has mean mu and variance sigma squared divided by n. Subtracting off mu and divided by sigma over root n, we have a random variable with mean 0 and variance 1, which I'm going to call z underscore n. This is a standard scaling process you may have seen before in probability theory. Now notice that the mean and variance are independent of n. It's always equal to mean 0 and variance 1. We therefore have a sequence over n of random variables, all with the same mean and variance, but each one consists of more and more random variables added together, more and more entropy. But we know that entropy is bounded about by the entropy of the standard bell curve. Is it possible, therefore, that the entropy of this sequence of random variables is always guaranteed to increase towards the maximal possible value, which is held uniquely by the bell curve? Indeed it is, and that's one way that you can prove the central limit theorem. I'm not going to prove this result since it's quite involved, but I think it's really neat and a plausible result. Other proofs of the central limit theorem involve things like Fourier series, and don't get me wrong, I love Fourier series, who doesn't? But this proof is a real beauty because we have an intuitive heuristic quantity, entropy, guiding us towards our limit function solution. As Shakespeare would say, brevity is the soul of wit, and we can sum this up as the central limit theorem is the second law of thermodynamics of probability theory. This may well also hint at why the diffusion equation in Brownian motion has a bell curve shape. So I think this is a good place to stop. We covered a lot. Hopefully this video has been useful in giving you an idea of how to interpret entropy as a measure of uncertainty, aka measure of information, and how pervasive it is throughout all different areas of mathematics. My advice to any mathematics students out there is to take all different courses that are available. They may intersect with each other more than you first think. Take pure and applied, statistics, mechanics, statistical mechanics even. All different topics, yeah. If you enjoyed this video, make sure to like, comment and subscribe. I've got quite a backlog of ideas that I want to start cracking on with, so make sure to look out for those in your subscription feeds. Thanks for watching.